Hello everyone, welcome back to my organic chemistry mini lecture. Today our topic will be the most stable chair conformation of cyclohexane. You may already notice that chair conformation of the cyclohexane. Okay, we call this chair conformation because it looks like it's like a beach chair. Okay, and that's why we call this chair conformation. And this is the most stable because all the carbons here has tetrahedral bond angle is 109.5 degree. That's the standard tetrahedral. No any ring strain in this chair conformation. That's why this is the most stable. And you can also draw the other type of chair. Basically, this is the mirror image of this chair. So basically, they are same thing, just symmetrical. And so in this mini lecture, I will just use this chair as example. Now, I will teach you how to draw this chair. Basically, there are three parallel pairs bond. This is one pair. This is another pair. This is another pair, parallel. So first, I will draw this bond, the single bond first, and then the parallel here. Make sure they are on the same level, okay? Horizontal, same level. And then we draw the other two lines parallel. Okay, make sure it's not flat, okay, it's tilted. And then the third pair of parallel, this one and the other one. So that's the chair. Okay, notice that, okay, none of this line are flat or vertical. If you did that, that's wrong. For example, you probably see this kind of chair sometimes, but this is actually not correct. Okay, so this is flat. No, this cannot be flat. So that's not right. Okay, so now we will talk about the different position on this chair. When you have the chair, when you draw a beautiful chair, actually there are two type of position. First is called axial, like this. See that the axial position is straight, okay, vertical. This is one, is point up. The other one is here, it's point up. And here is another one, point, okay, up, straight up. So that is the red colored. I show this the axial position. They are vertical and up. There are other three axial, but they are point down. This one down, another one from here down, and this are down. So there are six axial position, three up and three down. This one, this one, this one. I use red color to show this axial position. And the equatorial position are here. Here, equatorial is not straight up or down. It's tilted. So for example, this is down, it's tilted. Another one is tilted up. And this is a tilt down. This is tilt up. This is tilted down and tilt up. So all the blue colored are equatorial. And if you look at each carbon, they are all perfect tetrahedral. I just said in last slides. So that's why the cyclohexane will have the chair conformation as the most stable conformer. Now, red are all axial, blue are all equatorial, but there are three up equatorial, tilt up, not straight up. This one, this one, this one, and three of them are down, pointed down. This one, and this one. Okay, and this is so-called side view, or you can say it's more like a perspective view of this cyclohexane. If you look at from top, if you look from top, actually you will just have this 2D cyclohexane. basically just the 6-member ring here. So we call this top view. And sometimes the question will give you a top view like this 2D structure, but also show if you have substitution on this cyclohexane, they will use wedge, shows up, on dash shows down, and then how to draw the chair from the 2D structure. I will give you an example of mono-substituted cyclohexane first. This is a methyl group. From this 2D top view, actually this bond, it's point down. Since it's top view, if you imagine, if you look at from side, this is pointed down. And that's why, if you look at from this way, okay, side view, this help you find those up or down, axial or equatorial. Now there's a rule here. So if you have just one substituent, then that substituent must be equatorial. So if you look at this way, then this must be here, equatorial. That's down. It's down. You cannot draw that here, although this is also equatorial, but it's up. It's not right. So if you draw the chair first, 3 parallel, and then you can draw this methyl to here. Now, equatorial. That's the requirement. Also, based on this 2D, it's down, so it's down. So this is top view, this is the side view. You can also draw the methyl up, but that's not most stable conformation. Because if you draw the methyl as axial, then it will have steric interaction with this hydrogen and this hydrogen. And since this is all 1,3 position, so it's called a 1,3 diaxial interaction. So basically that is the steric repulsion. So that will cause more ring strain. So that will cause this conformation less stable. So that's why if you want to draw the most stable conformation, the only substitution must be equatorial, cannot be axial. Okay. Now if you look at this 2D structure from this side view, you can also draw the methyl group at left here, but must be down, must be here. If you look at this way, this will be your left side. So here, that's this down. Again, no matter what, this must be at equatorial, and this is down. So you actually have 3 choices. We just pick up this one, that's down, equatorial. We also picked up this one, is equatorial down. There's another choice, this one, it's also equatorial down. So you must look at from this side, from here. Then this methyl will be here. So you actually can draw 3 correct chair conformation for this question. Okay, so but next example I will not show all of them because basically the same. So but you do have 3 choices. Let's talk about the disubstituted cyclohexane, the chair conformation. This is the example with 2 substitution. This is isopropyl, this is methyl group here. Now they have different size. Okay, so let's talk about the order of those size first. T-butyl usually is larger than the other group. Now second is phenyl group. Phenyl group basically is the benzene or pH here. Now this is larger than isopropyl group. Isopropyl group is larger than ethyl group, 2 carbons. Ethyl group is larger than methyl group, just a CH3 here. Methyl group actually is larger than vinyl group. That's basically a double bond here. So that is the size order of the common substituents. Now, there's a rule here. We need to put the larger group to equatorial. That's a rule. Okay, now I will look at this side view from this side. And this is just to remind you those axial equatorial again. remember we need to put the larger here. Isopropyl group is larger than methyl group. So we need to put this isopropyl to equatorial. And at the same time, it must be up. So we can look at this position, those equatorial, where 3 up equatorial, 1 is here, 1 is here, 1 is here. So, and if I look at this side, I will have this isopropyl, this position. See, that's why I look at this side, because I can easily draw that isopropyl here. So it's easier to draw. So I draw the chair first, and then I put the isopropyl here. See, that's this position. And this position fit the requirement. It must be equatorial and fit the 2D structure. It's up. It's up. Now look at the other methyl group. If you look, the relative position is 1, 2, 3 counterclockwise. 1, 2, 3 is top view, side view. 1, 2, 3. That methyl group must be down. Down is axial because equatorial is up, so must be pointed down here. The methyl group here. So that is the most stable chair conformation of this disubstituted cyclohexane. So this is the rule. The largest group must be equatorial. What about the choice substituted? Our choice substituted cyclohexane, we have here, example is the T-butyl here, phenyl group, and the methyl group. And this is down, and this down, this is up. Okay, so again, remember the rule, largest group must be equatorial. Okay, so now, which one is largest? We know that order, so T-butyl here is largest, phenyl is second, and the methyl is the smallest group here. This way to look at this side view will be make the draw a little bit easier. Okay, so and then just remind you again those equatorial position. This largest must be equatorial and must be down. I found this is down equatorial. You also have the other two choice. This down equatorial, this down equatorial. But I will draw this way. Look at this side view from this way. So I hold this chair first, we draw the chair, and then this T-butyl group must be here because equatorial and it's down, basically this blue position here. So I'll draw this T-butyl group here. Then this phenyl relative position is 1, 2. 1, 2, he's here, it's down. The down position is here, so axial, down, point down. And then this methyl group is relatively 1, 2, 3, 4. Clockwise 1, 2, 3, 4, or counterclockwise 1, 2, 3, 4. So from this side view, 1, 2, 3, 4 must be here, or 1, 2, 3, 4. So this is up. This up position is here. It's equatorial. So you draw the methyl group up, equatorial. Okay, so again, the rule. Please remember the rule. Largest group must be equatorial. And the other group just follow the 2D structure. So when you decide which position to draw the largest group as equatorial, then that determined the other groups. And now what about tetra-substituted cyclohexane? 4 groups, or even 5 groups or 6 groups, always the same rule, okay? Largest group must be equatorial. So here we have phenyl, ethyl, methyl, and vinyl group. So we still have the order same, so phenyl group is larger than this ethyl, ethyl larger than methyl, methyl larger than vinyl group. So again, we can try to look at this side view from this way, and then this is to help you again identify those equatorial position. Now phenyl group must be up. So if it's up, then I see this position can be used. Also, you could have the other two choices, but I will draw that here. So first draw the chair, and then the phenyl, it's up and must be equatorial because this is largest. So here must be the phenyl group. And the other ethyl is 1, 2 position, clockwise, 1, 2, that's here. So you draw up, ethyl group. This is axial. And then 1, 2, 3, 4. 1, 2, 3, 4 is the vinyl group. It's down, so it's equatorial because the down is equatorial. And then this group methyl must be here. See, 1, 2, 1, 2 position. Remember, this is top view, this is side view. So methyl must be down, so I draw this methyl down because this is the down axial position. And the rule is the same. Largest group must be equatorial. Okay, so I will just give you these examples. You will apply this through to all kind of situation. Even you have more substitution, you always want to find the largest group. There's another situation if you have the same size. For example, you have a 2 phenyl group, then you will try your best to put at least one of phenyl group to the equatorial. If you can put them both to equatorial, that would be perfect. But if you cannot, at least one of the phenyl group, one of the substitution must be equatorial. You don't want to put them both as axial. That will be wrong. Okay. So that's all I want to talk about. I hope this video help you understand how to draw the most stable conformation of cyclohexane and the substituted cyclohexane. So if you have any questions, please let me know. Okay, good luck.